Hello everyone, welcome to Recitation 0E. My name is Peru, and today me and Koshali are going to give a brief overview of Pytorch, something you'll be using extensively throughout this course, as well as an introduction to tensors, the fundamental data type used in Pytorch. So, what is Pytorch? Well, Pytorch is an open source machine learning framework with an aim to accelerate the typical machine learning workflow and making machine learning more accessible. While it is widely known and popular for its deep learning capabilities, it is also a general purpose numerical computation library that can be used for traditional machine learning, scientific computing, and data manipulation and analysis. So the figure here represents what a typical machine learning workflow looks like. Most machine learning workflows will involve working with data, creating models, optimizing model parameters, and saving trained models in order to deploy them to a production environment for real world use. Well, PyTorch aims to accelerate this workflow by providing several useful abstractions. It provides deep learning primitives such as neural network layers, activation and loss function, and gradient-based optimizers. Provides high-level features for multidimensional array computing or tensor computing with support for hardware acceleration on CUDA-capable NVIDIA GPUs. Now all of this can be achieved by interacting with just the top-level API using just regular, idiomatic Python code without delving into the intricacies of the low-level operations. Also, this enables PyTorch to seamlessly integrate with other Python libraries like NumPy, SciPy, and scikit-learn, allowing users to leverage a wide range of existing tools and libraries for data preprocessing, visualization, and analysis. Also, as you will find out throughout the semester, computing partial derivatives or gradients is a central part of backpropagation-based neural network learning. Well, Pytorch's Autograd feature makes this process of computing multiple gradients of a complex computation easy by abstracting away the low-level details of gradient computation and backpropagation. For example, given two variables x1 and x2 on which you perform a series of operations to get z, as shown by the forward computation in the figure, with Pytorch's Autograd, the computation of partial derivatives of z with respect to x1 and x2 will be done correctly with just a single function call, even for very complex series of operations and program logic. Additionally, PyTorch also provides several domain-specific libraries that are designed to make it easier to work in various specialized areas, such as computer vision, natural language processing, and audio and speech processing. These libraries provide specialized tools and abstractions that simplify the development process for complex tasks in their respective domains. PyTorch also provides several tools and frameworks such as TorchScript, TorchServe, PyTorch Mobile, etc. to facilitate model deployment in various environments. So in summary, PyTorch provides an easy-to-use high-level interface which abstracts away many of the low-level details of numerical computation and hardware management, making it easier for you guys to focus on the deep learning workflow in your homework part 2s, on things like model design and experimentation, rather than low-level implementation details, which you'll be doing plenty of in your homework part 1s. Now I'll pass it over to Kaushali to introduce tensors, the fundamental data abstraction in PyTorch.
Thanks, Puru, for the introduction to PyTorch. Now we have created an exercise notebook for you to practice different functions that are available in PyTorch, which will help you in your assignments like in part 1s and part 2s. Make sure that you're using the following NumPy and Torch version in your assignment and for this exercise as well. We have linked the PyTorch documentation here, which you can refer to for this exercise and for your assignments as well. Now, this notebook has various tasks like interconversion, vectorization, and tensor manipulation. So, you will learn how to convert a NumPy array to PyTorch tensor and vice versa. You'll learn different vectorization techniques like outer product of two vectors x and y. Other functions include Adamar product, sum of product, ReLU activation function, which comes very handy in your part ones, and the derivative of ReLU activation. Similarly, basic tensor manipulation functions include flatten and squeeze, reshape, etc. So, if we want to flatten our tensor, that is, reshape the tensor into 1D array while maintaining the order of elements, we can go to the documentation search Latin here and look at the code. Similarly, this is what we'll do in our notebook as well. Torch.nn.flatten and return the output. And you get what you get the same answer as the expected output. We have also created a cheat sheet to help you out with all the main function that you'll require. But I do suggest that you go through the documentation as well and practice it with this notebook provided to you. We will end this video here, and you can check out other recitation as well on Pytorch for a more detailed overview for your assignments. Thank you.